All right, everyone. How are we doing today? Doing all right? Okay. I've not noticed that our post-holiday weekend in-class attendance is a little bit sparse. Hopefully, you all who are attending remotely are comfortable where you are, and had, of course, a nice reprieve, extra day in the weekend there. Okay. So for this week, we have two sections to cover to finish up the material in chapter 2. And after finishing up that material, we will be in a position to talk about what our first exam is going to be. Okay, so our first exam is going to be covering the material from chapter 1 and chapter 2. That really means that it's basically a test over chapter 2, because chapter 1 was some introductory material, and then we expanded upon the techniques in chapter 2 that were covered sort of as an introduction in chapter 1. Okay. The material that we're going to be discussing today in particular is going to be stuff that I'll give you a quiz and will involve technology in order to be able to work with, because it is numerical approximation based, and in order to do an instructive problem, one that's interesting enough to learn something from, we require sensitive enough computations that we wouldn't do it by hand. Okay. Or at least if we did it by hand, we would kind of do it in the painstaking way that we had to do calculations like this in the days before common calculators and computers existed. All right. So the sorts of things that you might see, say, in a recent film named Hidden Figures, if you're familiar with that, they didn't have terribly accurate calculators. So what they had to do was they had people whose job literally was to be a calculator, and they would by hand work out the necessary computations to the appropriate number of decimal places in order to get within their error tolerances to do their computations. And of course, one of the main parts of that movie was the central character performing a calculation in a way that was more sensitive than what the computers that they had set up at the time was capable of doing, in order to ensure that everything with one of their spacecraft launches was going to go as planned. Okay, so we're going to be talking about a variation of that kind of stuff, and in particular, we're going to be discussing something that is known as Euler's method. Okay, now Euler is one of those individuals that there's a ton of stuff named after. Okay, but this is another thing that goes on the list. The basic idea here is that there are going to be differential equations that we can set up. And we may not, by looking directly at the differential equations without doing any work, be able to figure out what the solution to those differential equations would be. Okay. For instance, on our online notes, which I'll switch over to here in a second, we have this differential equation. Okay, y prime equals y times the quantity 3 minus ty. All right, immediately we see that there's some problems with this in terms of the techniques that we are familiar with. If we were to multiply this out, we see that it's nonlinear. Okay, and by virtue of this equation being nonlinear, it is automatically beyond the scope of what we have solved in this course, unless we happen to be able to show that this thing is exact. And by looking at it, that's probably not the case, right? because exact equations generally look like this. Yeah. And everything over here is going to end up in the denominator of this. And I'm not going to have anything over here. So we're not in good shape. Okay, so it's not exact. But whether or not it was exact wouldn't impact whether or not the technique that we're about to talk about would be reasonable. Okay, so if we take a look at this differential equation, one of the things that we can do is, without knowing anything about what the solution looks like, we can always plot the direction field. Okay, and here I have made a plot of the direction field and put it on the screen here. And we see that the graph is kind of broken up into several regions, right? There's this region over here where the solutions look to just take off, right? These things all look vertical. We know that they're not actually exactly vertical because we can't have vertical slopes, but it means that the slope of the function is very, very large. Okay? We see the same behavior down here in the bottom right, except pointing down. Okay? And then in these other two corners here, the northeast and southwest corners, we see that there's kind of a region that gets cut off. Okay? There's this bump that we can see here. Okay? And there's another bump that looks similar that we can see on this side. All right? And what would happen is we want to come up with some way to at least get what an impression of the solution looks like based on the information that we can extract from the direction field. Okay? Now we could, by hand, go through and try to sketch loosely what a curve through this direction field would look like. But numerical computations can do this much more accurately for us, because what we can do is we can actually look at the actual slope at a point, right? And then draw some small line segment from one point to another using that slope. And then at that new point, draw another short line segment, and just basically make a bunch of small connected line segments together, and then use that as an approximation to the solution overall. The smaller the time steps we take, theoretically, the closer we would be to reconstructing the solution. Okay? And that is precisely how Newton's method, or Euler's method, works, excuse me. Okay, so most of the time this is referred to as Euler's method. It could also be referred to as the tangent line method. But the basic idea is that we start with our differential equation and an initial value, as we would, right? This doesn't work unless we're solving an initial value problem. We have to know some point that the curve is supposed to pass through, the solution is supposed to pass through. And then once we have that point, what we do is we use the fact that the derivative is equal to the expression that we have that depends on t and y. And this will give us the slope of the tangent line at a point. Okay? And then this is just the equation of the tangent line, right? If we move this y naught to the other side, it would be exactly this point slope formula. Y minus y naught equals m times the quantity x minus x naught, except instead of m, we have the slope at a particular point. Okay, so this is just the tangent line equation, rearranged so that it's a function of y. And so what we can do is we construct a sequence of connected line segments. It's not going to be a perfect approximation of the solution, of course, because the slope of the solution is going to be changing. But if we have small time steps, and stay away from the places where the slope changes very, very rapidly, we can come up with a numerical approximation to the solution. Okay? And so that is the idea. All right? And so this technique is employed on the direction field that we had previously. We start off at some point. Okay, the ordered pair that we start off with is here, -5, and then 5 times 10 to the -7. So a y value that is very, very close to 0, but is not exactly 0, because if y is 0 for this differential equation, the slope is 0, right? So we can't actually pick 0, but we pick a value very, very close to 0 so that the picture shows up nicely on screen here. But there is our numerical approximation for the solution. Okay, now it turns out that this particular differential equation is a class of differential equation known as a Bernoulli equation, which means that at some point in the future, we will be able to talk about what its solutions look like. But we see here the numerical solution graphed alongside the actual solution of the curve, the one that was determined analytically. And it's a pretty good approximation. Okay, the place where the approximation misses is the place where the change in the derivative is the most extreme, right? Which is what we expect, right? Our tangent lines are going to miss the most, the places where the slope is changing the most. All right. So I want to pause here for a second, because that's basically the theory for this section, okay, is how this works. And so I want to give you all that are watching or here in person an opportunity to ask some questions before we move on. You have a question?
Yeah, so is it just like Calc 1 where you do a function of that over the derivative of f plus h? Is that how the method works in Calc 1?
More or less.
That's basically what you're teaching right now.
Yeah.
It's just
We have a, well, it's, so what they, it sounds like what you're describing is a baby version of this problem, not the other way around. Okay, so you would, it sounds like you were applying, you're maybe doing something involving the secant line, or that the difference here is that, of course, we can have much more sophisticated formulas for the derivative, and we care about the t input and the y input, or the x and y inputs, however you want to think about it. I'm going to be using t as the independent variable here, but because it can depend on both. But that's more or less the idea. I mean, we're drawing tangent lines. It is the same formula. It's just that we have a more complicated version of the derivative to compute. And we may not do it the same way that you did it in Calc 1. It depends on how they decided to do the numerical part of this. All right. I'm not seeing any questions in the chat. So what we're going to start off with is doing this problem again, except showing kind of the pieces of how it works, and then going from there. But I have one thing that I have to finish making sure works. All right. Okay, I blanked out the screen. That was my fault. I'll fix it here in a second. Okay. So one of the very interesting parts about these particular numerical computations is that they can actually be done using a spreadsheet program. Okay, this is actually one of the best ways to do it, surprisingly enough. Okay, so let me do a little bit of work here in order to make sure that everything is as easy to read as possible. All right, so what we're going to do is we are going to start off with a t value here, and we want a y value, and we want a y prime value. And then over here, we're going to set an h value. Okay, so I'll come back to the screen in just a second. What we're going to be doing is our formula for Euler's method look like this, right? Okay, this is how we get from our current value of t naught y naught to our next value of t1 y1. Okay, so what we're going to be doing is basically using this method to generate a list of ordered pairs, and then that collection of ordered pairs is going to be our numerical approximation to the solution. So we're making a table. That's what we're doing. We're going to come up with a table of values that represents numerically the solution to the differential equation, or an approximation to the solution to the differential equation, more accurately. Okay? And so for the sake of simplicity, we're going to fix the difference in our independent variable. We're just going to call that h. And so that's going to represent the step size from one independent variable value to the other one. Okay? And the y values are just going to be whatever happens with the function. Okay? And the reason that we use spreadsheets for this kind of computation is that it allows us to do repetitive calculations over and over again, and also take the results from the previous values in the computation and then feed them into the next one. Okay? So what I want to do is use t naught y naught to find t1 y1, and then use t1 y1 to find t2 y2, and so on, right? The sequence of t naught, t1, t2 is easy to find because it's just this, right? Because I'm always stepping by h. Okay, so that one's not difficult to compute. But the other values are going to require a little bit more sensitive computation. All right, so we have our values here. Let's pick something not terribly small. Sorry, I need to fix this. Okay. It's displaying that way because there wasn't enough room. All right, sorry about that. Okay, so that's going to be our step size in between our t values. And for our curve here, we need to pick some initial value. We'll say that y is equal to 1 when t is equal to 0. Okay? And for y prime, this is where we use the formula involving our function. Okay? So our formula here is that the new y value is equal to the old y value plus, or sorry, we're computing the derivative, excuse me. Y prime is equal to y times the quantity 3 minus t times y. So what we need to do is come up with the numerical value for that, and then use the numerical value of that to feed forward through the computation of our new y value. All right, so we use an equal sign here to specify that this is a computation. We type in B2 because that is the reference to the cell for y, and then an asterisk for multiplication, and then 3 minus A2 because that's the value for t, and then B2 again for y. Okay, so this is basic spreadsheet program use. One of the things that I want to mention is that I'm using Excel for this because I have Excel installed locally on my computer. But if you were to go to the spreadsheet program in something like Google Docs or some other open source thing like LibreOffice or something like that, the computations that we're going to be doing and the way that you would type in commands is going to work the same in any of those things. We're not doing something complicated enough to require special features that are application specific. Okay, so this is all basic spreadsheet functionality. All right, so we put this in the computation here, and the value that we get should be reasonable, right? Okay, we get 1 for y times 3 minus 0 times 1. So we get 1 times 3, which is 3. That makes sense. Okay, now for the next part here, we need to compute the subsequent computations for these things. Now I want to increment t by h. Okay, what I can do is add a reference to this cell to that computation, right? Now, in Excel, if you press the F4 key, what it will do is it will put dollar signs in front of the row reference and the column reference. Or sorry, the column reference and the row reference. What this does is it makes it an absolute reference. Okay, so it always refers to exactly this cell instead of updating for positional arguments. Okay, I mention that because this thing we're going to want to update for positional arguments. So the y value here is going to be based upon our formula for y prime. Or sorry, our tangent line formula. So we want to do B2 because that's the previous y value, plus the value of the slope, which is C2, and we want to multiply that times h. Okay. And again, I'm going to make that an absolute reference. Okay, I'll double click it so it's easier to see what's typed in. Okay, so that is y naught plus f of t naught y naught times delta t, or h. Okay, do that. And then for y prime here, this is where we get to start copying stuff. The new y prime is going to be based on these two values, right? And if we grab this little slightly thicker thing on the bottom corner here, we see that our mouse cursor changes to a little plus. Okay, that is the fill marker. And if I drag it down, it autofills this formula, including changing the cell references. Okay. Now, that happened because it didn't have the $sign thing on it that I had mentioned previously. Okay. Because if I select all three of these and then copy down again, this still references the absolute reference that I made previously, but now points to the previous row. Same with this. Okay. So now what we get to do is for whatever t range we want to look at, drag this out. Okay. So the idea here now is that we should be able to make a plot of this. And I have to remember where I need to click. Sorry. There we go. I want to make sure I have the right stuff. Okay. And so this is a plot of the graph, the numerical approximation of the solution that we have generated. Okay. If we wanted to expand this chart, we of course could make more lines here. Have to be careful about the drag operation there. Okay. And then I think we could just do it this way. Yeah. There we go. Okay. We get something that looks pretty similar to what we had before, except it's graphed in a different range, right? Instead of starting way over to the left with a tiny, tiny value for y, we started with y up at 1, which impacted where our peak was going to happen and what the rest of the curve was going to be doing. But this is how the process works. Okay? The basic computation is always along this line. Okay? You start off with your initial values here. Okay? This is given to you from the problem. All right? You have your h value, which is again going to be given by the problem. And then for this, you use the formula from the differential equation to type in terms of cell references, the formula involving t and y. This value here is just taking the previous t value and incrementing it by h. each time. You're always just adding h all the way down. And then over here, you are using the formula for the tangent line. You have the value, the previous y value, plus the slope times h. Okay, and then lastly, and this is a repeat of the line above, you use the new t and y to compute the new derivative. And then that goes on for the next line. Okay? From here, we just start toying with things. You can make the step size smaller. Okay? Which theoretically should give you a more accurate solution, but is more computationally expensive. We need the same number, we would need twice as many data points to be able to still graph in that range from 0 to 4. Okay? I increased the h to, or sorry, decreased the h to 0.025, and we see now that our plot only goes to 2, whereas it used to go to 4. Okay, because all of the stuff in the spreadsheet was updated automatically. It's one of the benefits of doing things this way, is that if I decide that I need a finer set of approximations, I can change the h value and everything gets recomputed automatically. Okay, so on the quiz associated with this section, what I'm going to ask you to do is do the computations for a couple of different types of problems like this, 4 different values of h, and I want you to report certain particular values. So I'll give you a differential equation, I will give you a value for h, and then after I give you those things, then I will say, give me the value of y at 1 and 2 and 3, or something, right? For different values of h. Okay, you're going to get different answers for different values of h because it changes the quality of the numerical approximation. All right, and so you just give me the answers in kind of a form of a short table, and then attach a screenshot of something like this to demonstrate to me that you had typed it into a computer and used a spreadsheet to solve your problem. Okay, so a little bit of technology used here. Again, everything that I've done can be done using Google Spreadsheet or something like that. Okay, it all works perfectly well. And if you wanted to, not that you need to, I'm just showing that it can be done. All right, copying this is kind of a process. Okay. So another thing that we can do, just to be a little bit more explicit with what our solutions look like, okay, is this is our slope field that we've played around with a few times. Let's go ahead and reduce the range on what it is we're looking at here. Let's say go from -5 to 10 for that, and then this doesn't need to be nearly as tall. Why won't you let me zoom square? Or is it already square? Must be already square. Okay. So our slope field has a lot of stuff going on, kind of tight in close to 0, right? So maybe we want to look at this from -5 to 5 in the x range. Have to change this value to get that. And then from here, we can also pull this in tighter. Doesn't have to be exact. Okay, anyway, still kind of a mess, but looks okay. Now, the reason we do all that, of course, is because one of the things that you can do in Desmos is if you have something that you've copied from a spreadsheet, you saw me copy the big list of numbers that we had, you can actually paste that table into Desmos and get the curve for the solution here. Huh? I discovered it because I spent quite some time trying to figure out how to do this demonstration. And someone finally mentioned, it's like, well, you can just paste a table of values in there. So it's quite neat. So of course, this gives me more motivation to maybe go back to our spreadsheet and get a wider range of values to give me a better table to be able to paste into Desmos to match up with our direction field, because making a direction field in Excel probably isn't what we want to try to be doing. That's not great. There are other programs that we could use that are better at drawing direction fields, like Python is a programming language, and the images that show up in the notes that I've shown, those were made in Python. That's not something that I expect you to know how to use, so we'll stick to more accessible tools. Okay. So what we want to do now is maybe change this to -5 and this to some small number, because it's going to have to be small in order for this to fit on screen. So we'll use that. We're getting numbers here because this is just being silly for the numbers display, but it knows what I meant. Okay. And so we see that all of this got updated. Now, in order to get a range of values that goes out for a while, I've got some dragging to do. Let's see where we are. Okay, that's way too much. But at least we have enough. Okay. So now we can go here, go back to the top. We can copy this, kick back over to Desmos, paste this in, and get our picture here, which looks very similar to what we have here. The graph should look the same because well, I think it's the same. Same initial condition, and I think I changed H to be the same value. Just go home, Nathan. Sorry, there's a keyboard shortcut to go to cell A1 in Excel, but I don't remember what it is. Okay, sorry. So we don't have exactly the same thing because our H value in Excel is 0.02, but we'll call that close enough. Okay. So what I want, again, is for you to use a spreadsheet program in order to do the computations that I ask you to compute on the quizzes. Okay. Follow along with this process. Okay. And if you want a more condensed version of this discussion, I go through and do a video example of a different problem, okay, that you can follow along with. So that is available online as well. And if you happen to be interested in the Python code that was used to generate the figures that show up previously, this is on the webpage as well for you to play around with. Okay. The Python stuff is completely optional. It's just where this picture came from. Okay. So if you have a little bit of programming experience already and are interested in playing around with that, that's available for you to take a look at. If you're not one of those people, you need not worry about it. Okay. So I want to pause here again, ask for questions, see how people are doing. Everything's all right. Okay. I'm gonna be bad and take a drink of my soda. So give me a second. Yeah, I don't want to have a mess. I'm sorry about what happened with your Dr. Pepper earlier. So I have a high school teacher who was an eccentric fellow, one of those guys who just every once in a while start yelling about whatever nonsense is going on. And he had been a teacher for decades, like getting close to the 30-year mark, and swore up and down that the only kind of soda that had ever been spilled in one of his classrooms was Dr. Pepper. And I was in his classes and people spilled soda and it was always Dr. Pepper. It was hilarious. The most funny time, though, was I was in a classroom that was next door to his classroom in AP history class. It was the class that I was in. He was teaching. I'm not exactly sure what his other class was, but we were just sitting there and we were covering something about, I think it was Reconstruction or something. But we heard someone yell Dr. Pepper, and of course it was this teacher at the top of his lungs because someone had knocked over their soda. So, anyway. Alrighty. So, Dr. Pepper spillage aside, for this section, there isn't really much more for me to say other than to ask you all to go practice. And if you have questions that come up for 2.7, to let me know so that we can work out those things. Okay. And what we will go ahead and do to take advantage of at least a few extra minutes to get things going for us moving forward is talk a little bit about the final section from chapter 2, which is section 2.8, as soon as our math renderer stops freaking out. Okay. It always loads really slow when I'm streaming at the same time as loading the web pages. I don't know why. Anyway, so there are two main pieces of content in section 2.8. One of them is a restatement and a reminder of the existence and uniqueness theorem that we had earlier on in the chapter, okay? And the other bit is an application of this idea. Okay. So looking at the notes page that's on screen, this right here is the operative idea. Okay. What we're going to be working with is something known as the method of successive approximations. Okay. In section 2.7, the one that we just covered, the approximations to the solution that we were generating are numeric, right? We were using a computer to aid us in the process of coming up with a reasonable, under certain assumptions, approximation to the solution of the differential equation. In this section, what we're going to be doing is constructing a solution step by step. We're going to take advantage of our existence and uniqueness theorem, okay? And also the fundamental theorem of calculus, basically, okay? And instead of thinking about a differential equation in terms of derivatives, we're going to be thinking about it in terms of integrals. And use integrals to build up from our initial value a solution to the initial value problem. Okay? So, this differential equation here is the same differential equation that is dealt with numerically in the video example. Different initial condition, but it's the same ODE. Okay? But for this problem, what we want to do is attack the differential equation in a way that makes it easy to work with on the level of integrals. Okay? Now, the purpose of this subsection in the notes is to show that if I don't have a differential equation whose initial value is 0 at 0, that I can always do the necessary algebra and calculus to transform it into a version of the differential equation where the initial condition at 0 is 0. Okay? So, we're going to be doing a lot of integrating. We want our lives to be as easy as possible. Our lives are as easy as possible if the initial value is 0, 0. Okay? So, in a lot of the problems that show up for this in the textbook and exercises, they're going to give you 0, 0 as the initial condition. Okay? Otherwise, there is a short process to go through in order to make sure that you adjust the initial parameters as necessary. And basically, it breaks down to shifting everywhere where t and y shows up, right? We have the t value is 1 and the y value is 2. We shift to the left 1 and we shift down 2. That's it, right? Okay, so sometimes a slight change is necessary, but ultimately it's not a big deal. Okay, so the way that this works is we have our initial condition 0, 0. Okay, so we make that change if we need to, and we have our differential equation. It doesn't matter if the equation's nonlinear. Okay. And what we're going to do is we are just going to start integrating. Okay. And each time we come up with a solution, we're going to take an integral, we're going to get an answer, and then we're going to plug that answer back into the integral. And we're going to do this process until we have computed a sufficient number of terms to guess at what the solution may look like if we were to keep computing terms, okay? Ideally, we want to identify a pattern, okay? let's start with this example here. Okay. Let me switch over to another screen. All right. So we have our expression here. Now, just the point of what we're doing is we're taking advantage of the existence and uniqueness theorem. Okay? We are saying that y is equal to sorry, let me be more specific about that. We're saying that there's a function phi of t that is equal to the derivative from 0 to t of f of s phi of s ds. Okay? Now, this is something that we're going to have to get used to. This is one of those funny fundamental theorem of calculus integrals where the s in the integrand is just a dummy variable, right? Because I want to produce a function of t, I have to put t in the limits of integration, which means I have to have a different variable for my integrand. Okay? What I want to do is I want to come up with a sequence of phi n's and I want in the limit that sequence to converge to phi. Okay? So phi is the limit as n approaches infinity of the phi n's. And if we do things right, then that should be the solution to the solution to the initial value problem. Does that make sense? Seems okay? All right. Now, one of the ways that we force this to work is that every individual element of the sequence has to satisfy the initial condition. Okay? But we know that there is one and only one solution to the initial value problem, right? So none of the candidates prior to getting to the limit of the sequence are going to be the actual solutions. And this, even though we haven't proven the result, is what guarantees convergence. Each of our approximates obeys the integral equation, the integral version of the differential equation, right? And satisfies the initial value. Okay? And so that's what pushes it into being what we're looking for. All right, so let's start working this out here. We'll do blue, I'm tired of black. Okay. The first guess that we always make for phi sub 0 is 0, because that's the simplest function that satisfies the initial value. Okay? So you always guess phi of 0 equals 0. Phi 1 is a matter of doing the integral. We integrate from 0 to t. I'm going to write it like this to be as explicit as possible. Okay? You plug in the previous guess, and the previous guess is a function of s. All right? I didn't write it, but I should have. Okay? Each of these, sorry, I made a mistake. This is the variable stuff that is confusing, which is why most people just leave off the variables. Okay, sorry. This is a function of t, right? Inside the integrand, we write s because we're integrating with respect to s. Okay? It's very easy to mess up, all right? But it matters the most when we're going to do what we're about to do, which is apply the initial conditions. Okay? So let's first simplify this expression by plugging in our values. Phi of 0 is 0. So there's nothing exciting going on with this computation. Okay? And so we integrate 2 with respect to s. We get 2s. We need to evaluate that from 0 to t. 2 times t minus 2 times 0 is 2t. Okay? So this gives us our expression for phi 1. For phi 2, play the same game. 2t times, 2 times the quantity, 2t plus 1, 2s plus 1. Talking and writing, it gets me every time. Okay? Again, maybe I should write that as the second step. Two times phi 1 of s plus 1. And you plug in phi 1. Distribute the 2. I'll use an extra line here. Evaluate at the endpoints and get this expression here. Okay? We keep going. Point is to compute enough of these to get an idea of what it is we're looking at. So now we have phi 3 of t is equal to the integral from 0 to t of 2 times the quantity, 2s squared plus 2s in parentheses plus 1 ds. Distribute the 2 again, compute the integral. We're going to get 4s squared plus 4s plus 2 ds. And integrating and then applying the initial conditions because we know that the zeros are just going to disappear, right? We get 4/3 t cubed plus 2t squared plus 2t. Right? Now, maybe you've started to notice that this is going on. Okay? That in some sense, the answers that we are generating here are accumulating. Okay? And maybe in general, for some number of these problems, that's the way these things go. What we would like to do, if we can, is identify the pattern that is developing as we're performing these computations. Okay? And we want to know what we're doing here, right? I think it's pretty clear that we have a factorial term showing up in the denominator. As a reminder, that's what the factorial notation means. And in the numerator, we have something going on with some power of 2, right? Does that match up with the answers that we've gotten previously? It does, doesn't it? 2 squared is 4 divided by 2 times 1. So 4 over 2 is 2. Yeah, this one it's, yeah. So this is 8 over 6, which is the same thing as 4 over 3. So that checks out. And then this last one would be 8 over 12, which is the same thing as 16 over 24. Or sorry, I said that wrong. Yeah. Okay, so what that's saying is that if we were to go all the way to the nth term, that it looks like this, right? The sum from 1 to, sorry, I messed that up. I need to change letters here. I apologize. Those are K's now, Nathan. Sorry. K equals 1 to n, because I use the lowercase n as the indexing for phi n. Okay? And so this expression here would give us the numerical approximation to, sorry, an analytical approximation to the solution to the differential equation. And I ask you, students who have supposedly taken Calc 2, what is this? It's a series, right? Okay. And if we were to take the limit as n approaches infinity of this expression, we have a Taylor series. We hope, right? Certainly looks like a Taylor series. Okay. Radius of convergence is probably decent because I have that factorial in the denominator, right? We could, if we were diligent, of course, use the ratio test to determine what the radius of convergence was. Okay, I left off the limit notation. Need to be better about that. So we got a 2 in the numerator. Times this, right? Limit 0 for all t. Sorry, I wrote n instead of k again. Sorry, this should have said k. The limit depends on k. We have 1 over k basically in the denominator. The limit of that is as k goes to infinity is 0. And there's no dependence on t in the limit, right? So our radius of convergence is infinity. It means that if I add enough terms, I will eventually get a perfect reconstruction of the solution. That obviously is expensive because I have to keep adding terms the farther away from 0 I get. But I could, in principle, approximate to an arbitrary precision. Yes.
In computational math, we use Taylor series a lot for trying to find the exact roots for specific problems.
Okay.
And so I was just thinking we talked about this a lot in there.
Okay. Having a good background with a Taylor series is very helpful. We use it in precisely this way for this section here, and then in chapter 5 we'll be doing other things with series that are more explicitly can only be done with series once we get there. So good to have some extra practice. Okay, so I realize we're out of time, but I wanted to kind of go through this so that there's a little bit of buildup prior to next lecture, where we're going to be doing some more examples of this so that we can see the process, that I can go through the mechanical part of the computations a little bit more quickly. These problems, of course, are on the tedious side in just terms of there's a lot to write down and go through. And of course, also on the web page for the notes, there is the computational work that we just done. That is typed out and done kind of in a more deliberate way to show the pattern emerging as it does than what we did in practice. What we will be doing in these computations when we're working them out by hand, of course, is trying to not hide the details and not simplify all of the arithmetic all the way, because we want to be able to track the patterns that might appear in the coefficients. Okay, the idea is to see if we can identify a pattern, and if we can, to see if that pattern matches a Taylor series of a function that we're familiar with. Because if there's something that ends up looking like an exponential function, which happens to be the case for the example that we just did, even though we haven't written down yet, we want to notice that and then be able to say, oh yeah, this is just e to the 2t. Because that's what we have, basically, is e to the 2t that needs to be adjusted by a constant. Because we didn't have the k equals 0 term in our expression, but we've got the rest, right? And it turns out that this is the Taylor series for e to the 2t minus 1. Because I need to add in the k equals 0 term. All right, so we'll pause for there. We'll have a quiz that'll get posted later in the week for everyone to work on, and then we will try to do some more examples of this in class next time, having already talked about the theory part of it here. All right, enjoy your evening, everybody. Take care, and I will see you next time.